Okay, let's get started with lecture number 1. And this lecture will introduce you to the course. What I did for you a few minutes ago was go through the syllabus and all the boring part, where we have to, be students and figure out what we have to turn in, when we have to turn it in by, and show up to class and stuff like that. So this purpose of this lecture is to orient you to the concepts, and it's actually more than just an overview. I'm going to talk about and cover the differences between distributed computing, the internet, and client server in this lecture as well, and also go through the concept of tiering, web tiering, and also the basic core concepts of what would be considered the enterprise. And we'll look at some design patterns, and it's actually more than just an overview, although there's also an overview in it as well, so it's pretty complete. This will take us about an hour, so then we'll take a break after this one. So what do you need to know for this particular class? Java is an essential. It's not necessary to understand the different packages as well. You don't have to know anything about data structures either. You're going to want to know something about relational databases. If you've taken a relational database class before, or if you've taken my Oracle class, you're in great shape. If you haven't, don't worry about it. If you're a fast learner, most of the stuff we're going to be doing, I'm going to give you the SQL queries for. And we'll see, probably not till after lunch, we'll see JDBC in action, and you'll see how you can cut and paste and use it with a really nice kind of web interface. You don't have to be an Oracle or a database expert, but it is nice to know something about relational databases as graduate students, and especially in CE, computer science or software engineering. I would hope that you have had a database course before. Understanding how to do stuff is easy. How to use how to use your Java background when you need to review for some basics, perhaps. Not a bad idea to kind of refresh, but a lot of you have just come out of my object-oriented programming in Java course, so you're already in good shape. So this is really a comment directed at people who haven't taken Java in centuries, who just didn't come out of their last class, and maybe you have a C++ background instead of Java or something like that. So why you're here? This is the hottest new technology. This is your sales pitch. That was it. Hottest new technology. No, it's not really new anymore, actually. It's not really. In fact, I don't know if I'd call it hottest either anymore. I think mobile phone development's probably beating it right now. But companies still have a need to build enterprise-wide applications, and we'll see what that is in a few minutes. But experience in a Java EE, or even familiarity with it, these gives you, in fact, when you're done with this course, you'll have at least 5 or 6 buzzwords that you can put on your resume. You can put RMI, JDBC, you can put Java Beans, servlets, you can put database, server database connectivities, all sorts of different buzzwords you can stick on your resume now. So it's not a bad class to take for job skills. And obviously, you're not learning really an application in this course. We're going to be focusing mostly on the concepts, but you'll be learning the application stuff at the same time. So it's more of an academic versus let's play around with the EE software. So it's not like a software course. It's a concept course as well. I'll start with the concept of the application server, and this is where we begin our architecture lesson. So what is an application server? What is it? A simple server similar to a web server, provides middle-tiered logic for enterprise applications. So the applications that you're building in this course are applications that would reside on an application server, not on a desktop computer, not on a client computer. They could, however, when you're developing, appear on a client computer. So what we're looking at is it's just, they do more than just web page service, provide middleware support for web applications. So if we think about web servers and application servers, there's a big difference. Web servers usually have a port that serves up HTTP interface protocols for web content, HTML content. We can also get JSP content through there, ASP content. All sorts of different scripting languages work through there. Nice. However, it's mostly static, a little bit of dynamic. It's not what I would call application level. That's more web surfing level or web enabled. And we have a special server for that. It's called the web server. And the web server is normally the front end for the client. So you're the client, you're at home, you have your client browser, your the Internet Explorer, like a Firefox, that's what I was thinking of, browser. You're connecting first to the web server. The web server connects to this application server. The application server is the one that's providing the functionality for the true application. The application server can be used by not only the web server interface, but also the intranet and the people that are working on their desks running applications. It could be the same applications, and in some cases it is, depending upon the type of application it's running. We also have back-end servers. I would call the web front-end, web server. I would call the database back-end servers back-end. And we have a tiering that occurs. So we don't have just one kind of client server. We have an end tier, any number of multiple tiers, specifically designed to host applications. So here's an example of application servers, a web page with a submit button that invokes a Perl script or a Java class. It could be served by a web server on the front end. If the Java class used some data from an enterprise database, let's say maybe it picked something from Oracle, we could take the web page and connect directly to Oracle, or we could share it through another application and interface to it. So the class might be better implemented in an application server rather than in a web server, because we have to think about security, we have to think about tiering in terms of the design and the design pattern that we might be interested in creating. And this is where the enterprise comes in. So the enterprise is a matter of taking everything and separating it out into different components, putting the components together and assembling them as a system. And the system involves customers, it involves suppliers, it involves internal and external entities and other systems. And it really becomes a really big internetworking type of application development environment. So the technology that we're using, we have various different levels of technologies that exist within the application server itself, and this is where that terminology end tier comes into play. Usually it's considered end tier, meaning that there are many transparent clients, servers, everything that works together. And what I'm going to do is kind of hit you with some buzzwords and things you may or may not be familiar with. The HTTP server, that's the web interface, the web application. The Enterprise Java Bean server is back further in the hierarchy. That's going to be more of your application level. Your JDBC is going to be your driver interface, and we'll go through that today. Your JNDI as a definition enables you to find, it's a name, lookup, find other components within the enterprise system. It's more of a directory service or interface, I should say. Servlets as a concept, so it's Java's answer to the traditional CGI with advanced ability to stay connected. And it gives you persistent data in the server between the different calls. And this is kind of one of the concepts and the focuses of this first lecture, is to sort of review your networking background, and so that you become familiar with some of these terminologies, but also the underlying concept. In the old days, before we had Java, and if you're thinking about, well, how does Java fit in? It's sort of like .NET, actually. If you think about it, .NET's providing almost the same thing. And what it's giving you is transparency. Transparency between the different levels of the tiers. So the web server that connects to the application server, you don't know. It seems like it's all on one computer. So the transparency gets rid of the separation, puts it together, makes it into a big picture, I should say. And before we have Java, before we had middleware or the concept of .NET or any of the other JVMs that are out there, machine virtual environments, we ended up having what was called a strict client server, which is sort of the beginning of computing in general. And this is coming up, but I'll talk about it now because the word CGI, and some of you probably have heard CGI, Common Gateway Interface, but you may or may not have ever used it before. I would hope that you haven't and that you're using more current stuff, although it's not a bad idea to be familiar with the concept, which is why I'm going to take a few minutes and explain it. The client-server traditional model was stateless. We had a client connected to a server, got something, sent it back to the client. More modern technologies, not stateless, they're persistent. So persistent data maintains sessions, maintains connectivity, but doesn't have the same workload as a constant connection. So we have a whole stream of clients out there that appear to be connected, that are connected, but it's not taking up a lot of bandwidth. One of the problems with a client-server environment in the old days, and we still have sort of a client-server architecture that's going on, but in the old days, when the client connected to the server, if we go back to operating systems 101, every time anyone logs on to anything, it creates a process. And every program that runs creates a process. And that's how programs run on Unix, that's how programs run on Windows. All process-oriented. The more processes that we have running simultaneously on a computer, the slower the computer's going to run. Because the processor has to schedule those processes, and it takes up resources, memory, CPU cycles, it takes up everything. So if we had 1,000 clients on the internet, as an example, and they all connected, this is pre-internet by the way, if we had 1,000 clients simulating our internet, they all connected to the server, that server is probably not going to be able to handle the load because it's almost like 1,000 simultaneously people all logging into one Unix box. And depending upon the power of the Unix box and what the application was doing, it may or may not actually load it. So we had server farms. Tons of servers. They all do the same thing. But you log into this one, you log into that one, you log into this one, break it out. Expensive. Very expensive. And not very efficient. And the way this was actually being performed was through this traditional CGI. CGI is Common Gateway Interface. It allowed from a web HTTP protocol a doorway to go into a directory that was on the server to run a program on the server. That's all it did. And these programs were written in C++ and Perl and Python. CGI actually supports a multitude of traditional programming languages, not web programming. And it had nothing to do with the web, because this was essentially a way of a server serving up and providing functionality to a client of something it had, and it created server-side applications. Very old, very antiquated, because let's say, for example, you have Hello World running this way. Every client who logs in, who gets this, goes through the gateway, has their own process set up and their own version of Hello World set up. And you can possibly imagine the bottleneck that might occur at that point, because there's no economy of scale. You know, it's just everybody is going to take up resources. And it doesn't run very quickly after a while. So it depends on how many processes your server can actually handle simultaneously. So then middleware came around. Middleware said, well, let's provide a platform that allows multiple clients to come in, and instead of going through and each client acting like a separate entity in itself, let's provide an environment to give them services and to provide these features not only of security, which CGI actually lacks completely. There's no security with that. So let's give them security, user management control, transaction management, session management, you know, all these kind of services that went along with the middleware to provide transparency and a better solution to CGI in terms of making things persistent, making things actually not take up as many server resources. So then RMI starts out, and RMI is remote method invocation. So when you write a program, and you're already familiar with RMI, actually. If you've ever written a Java program, you've done method invocation. Well, method, object. You've created objects, you've made instances of objects. If you've ever written a Java program, you've already done this, actually. But you haven't done it remotely. So in this class, we're going to take and do it remotely. How you do it remotely? You install RMI on the server. And RMI takes and serves up objects. So on your computer, if you have 5 clients, 5 client computers, 5 people run the program, we have 5 different instances of objects, 1 on each one of the 5 computers. So take that one object, put it on the server. We have 1 instance of 1 object, have the 5 people connect remotely to the server. Now they're all using that 1 object. So it takes away the problem of the inefficiency of CGI, where CGI, every client who connects has their own session, has their own process, has their own, the server's doing work individually for 5 people. Take and get rid of all that overhead. RMI makes it so it runs faster, makes it more efficient, makes it so that there's security among which client can access which object. In the CGI world, anyone who wanted to, as long as you knew the name of the file, you could actually probably run it. and no security, no protection. You can upload, download. That CGI interface is just an open door, essentially, to the server. RMI says, well, let's create an RMI manager. We'll have a session manager. We'll have an app, we'll have transaction managers in there. We'll have security managers, and we'll set this all up so that when a client comes in, they get served up a method from an object that already exists, and then that object can give them and the method can deliver the functionality that they're looking for. So they're all running one program. They're all using one object. So kind of came in handy. And then we ended up with this thing called server beans, or actually it's on the next slide, but I'm going to talk a little bit ahead because it kind of fits into the same concept, big picture. Then we have beans. Well, what are beans? Beans are small little Java programs that create things like connectivities to databases, and they do functionality, and they do programs, and they create, they're basically objects in themselves. So if we create beans and we stick them in a server environment, unassociated actually with RMI. RMI is kind of a different tool that we can use with beans or without beans. It doesn't really matter. We can mix and match all of this stuff together. In fact, it is done for different purposes. But the bean technology says, well, all right, so if the client's going to connect to the server, let's have a bean go out and connect to the database. Why do we want 2,000 clients to connect to our database? That's a lot of hit on the database. So let's create a Java bean, put it in the server, or servlet. I'll talk about that in a few minutes. Have that guy, his responsibility is to connect to the database. One central connection point, less problems, fewer problems with security issues and things. You don't have 10 million clients hitting on that database constantly. More control over the session information, more control over the use of the database. Streamlines it, and then you can tier it. And so we'll see in the next couple of slides some tiering examples where we separate the functionality. If we can do that, then we have, again, more efficiency, and now we have more efficiency on the application server, is what we're essentially creating. So JSP is like ASP, but it's the Java version. So if you're a Windows programmer, you already know about ASP. ASP, what is it? It gives you application level functionality from a web page. It's used to create web pages, but they're more than just web pages. They have application features associated with them. It's a JSP is the same thing. Allows for embedded Java calls, similar to PHP, similar to C, used for the presentation layer, presentation of the data. So JSP script can go out, populate from a database, can go out and connect to a Java bean, get the information from the database, bring it back, populate it into an HTML interface on your page, essentially. Works with HTML just like PHP does, actually. If you don't have a web programming background, don't worry. You're probably going to be interested in taking a web programming class after this one. So here's how it fits in. You learn the Java EE, you learn the RMI, the JSP, and then you have to have something. You need to know how to write HTML code eventually, because you got to show something, and that's where the presentation layer comes in. You got to show something to the user. You don't have to be a graphic designer, but you're going to need to know how the pieces work together, whether you do that job or not. So it's not a bad idea to take a web HTML class, only because it'll kind of give you that front-end information that you're going to miss if you don't. And here's what I was talking about before. This enterprise Java beans up here. It provides the business logic and database connectivity. It's used a lot for database connectivity. We're going to see JDBC work without beans, and then I've got some programs that will actually take and use it with beans. So you can kind of see the with and without kind of thing. Depends on the application application environment and the resources that are available. This allows sharing of the resources between many different applications, can all use one bean as the connectivity between the applications themselves and the database. So that's why I say the beans are kind of small little programs. One bean might just have one function of connecting to a database and providing connectivity services. And that's, it can be used for other things as well. It's not limited to just databases. RMI allows separate Java applications layers to communicate with each other. It's a level above sockets. We're going to talk about sockets today as well. And then we'll be creating sockets with UDP and TCP, and we'll kind of see how that works together. It's nice to have that little background, only because now you understand. You can't go through a networking class or Java without knowing what a socket is. It's just basic. JMS, we'll look at this. We'll look at JMS in the next weekend session meeting. It's the messaging, Java messaging, newer technology, provides a publishing, subscribing, point-to-point framework. So why use Java? I've actually covered most of the main points on the EE already, actually, when I was talking about the pros of using the tiering environment. But outside of others, such as comparing it to Visual Basic, which is, actually Visual Basic is used a lot because of the ASP.NET for web development. In fact, Visual Basic is probably the easiest for IT, information technology or information systems. True programmers would probably be bored with that, but you know, Java's more along your lines. C++, Pascal, Prolog. Java gives us the portability, especially with web applications, cross-platform compatibility, as we're all familiar with. One standard, which is interesting. If you learn the EE platform, compare it to .NET, in the last 5 minutes when talking about .NET, I've mentioned ASP, Visual Basic, well, there's C#, there's Visual C++, there's so many different languages and they're like not very similar. Everything in the EE platform is written in Java. Your beans are written in Java. Your JDBC connectivity is written in Java. It's all one language. So you learn one language and you get all these other tools that go with it. All the servlet stuff, written in Java. Everything is written in Java, which means you got to learn Java. It deploys on all of the leading web servers as well. Every web server out there. What does .NET deploy on? Microsoft servers. Limited, which is why Java is, you know, if you're going to limit, you know, which is, I don't know why, you know, anyway, we're not going to bash on Microsoft. I'm not a huge fan, obviously, but you've got more flexibility, and it's open source, open development platform, and it's built on Unix. I mean, it runs perfectly nice on almost any server. So Java has defined the standard APIs, protocols for server communication. Keep it open, and now that Oracle is owned by Sun, we have better JDBC drivers that are written specifically for Oracle, and we've got better Java support for it. It runs extremely quickly and fast, and you know, just so much. There's so much support, so much growth all in one house. It's nice versus the Microsoft route, but Microsoft does have a purpose, does have a use. So, but this isn't a .NET course, so take a .NET course, and you'll learn all the good stuff about that. And what is this? Just more in the sales pitch. Why use Java? Provides single technology. I think this is actually kind of a repeat here compared to the others. This is an example here. If you're using the CGI, you've got Perl, you've got C, you've got all these other languages and things that are going in with it. So this is just a little checklist on the technologies, and then it's called a review, tech review. I'm just going to slide through this stuff because it's kind of boring. But on the client end, we're looking at HTML. Applet's not really used very much anymore. Yeah, they're kind of slow, kind of sluggish. I would, if you're just getting into this, I'd stay away from applets. They're a thing of the past. Java applications, no, they're a thing of the future. Visual Basic, actually, for client applications is pretty popular because it's easier to use. C++ is also still very popular these days. Delphi, scripting languages. I would say that the scripting languages, PHP, Cold Fusion, stuff like that. JavaScript, JavaScript, VBScript, not so much anymore, but JSP is probably a little bit more popular because the more you can pull away from the client, put on the server, and pretty much the direction is all server these days. So this was a kind of a review of client-related software programming environments. On the web server end, this is where we're seeing most of the growth, actually. JSP, ASP, servlets, PHP, Perl, C, CGI, kind of outdated on the bottom of the list here. Because think of this scenario, clients, if you go back to your first internet or first networking course, you learned about thin clients, fat clients, servers, client servers, stuff like that. We were starting out thin, we had those dumb terminals, that connected to a network, and then we got all fat. Now we're going thin again. So the entire client environment has done a 360. We've gone from thin to fat, we're back to thin. And what I mean by thin is we don't want a lot of power on the client side. We don't need a hard drive. We don't need anything. We just need a screen and a keyboard. That's as thin as you can get. The fat stuff is like this computer here. It's got a 200 gigabyte hard drive. It's got RAM on it. It's got a screen. It's got a graphics controller. It's got ports for everything you could possibly imagine, and it takes in data from all different areas. Your tablets, your phones, those are kind of thin. Actually, some of them are a little chubby. Some of them are getting fat, but they're thin. And the thinness you can go, if it's not on the client, where's it got to go? On the server. So the growth is actually in server technologies to provide for streamlining fast clients that can be thin. So you don't need a lot of processing power on that client to run the application, which is great because now we have all these cool applications that are going on our thin clients. Databases. This is just a little tech review. I can kind of skip through this as well. Relational tables, primary keys. These are some of the things you probably want to be familiar with. Transaction blocks, actually more so than anything else, because the concept of the transaction, and I'll cover that in the class actually, so you don't really need to know very much on that as well. So that was, believe it or not, just the review of what we're going to cover in the course. So this is our start, and I'll go a little bit longer here. So this is the client, server, and distributed systems and overview. So here's your networking overview as promised. So what's the internet? Distributed. The internet is a distributed computing environment. It's also client-server if you think about it in a lot of ways. What's the first thing you do as a client? You connect to a server. It's your ISP. It's your point of entry into the internet. You're going from one server. That server is going to go to another server. That server is going to go to another server. You're going to go to many different servers. You're still a client. You couldn't, however, you could actually be a server even though you're a client. So the concept of multiple clients connecting to a server still exists on the internet, but so does distributed computing. And distributed computing comes from the old Unix days, actually Unix days, where you take one application and you run it on multiple different computers. So you go to barnesandnoble.com or amazon.com. Who knows how many servers you're actually working with? I would almost say probably more than a dozen servers that you're going to interface with. And they're distributed. So the shopping cart you're using is on a different server, than the database that you're searching for your Pearson's How to Program in Java book, or for your whatever book you happen to be looking for, versus let's say you decide, oh, let's check out the used options. Going to be on a different server. What we have are multiple servers that are distributing the processing, distributing the applications, distributing the functionality, but providing you the transparent server that you're connecting to. And then that distributed environment, that server that's housing, and this is the interesting phenomena, the server that's housing up the list of books that Pearson's offers Barnes & Noble's is probably the same server that's being used with Amazon. Probably the same server that's on eBay, probably the same server. So it's shared among multiple different applications. And what is it? It's probably a database server that's keeping a general index of everything that the publisher has in stock. So you buy it from one site, and it's coming out of the same database, probably coming from the same publisher as you bought it from another site, or you bought it from another site. And so companies are starting to get wise about this configuration, as some of the successful internet companies have. And you design your application like this. So let's say you have a retail store, and you have an inventory. Why should your retail store be different than your web store or other store? So if you house everything on a database server that's distributed among all of the different applications and everybody shares the same database, then you never have to actually be out of date. When someone buys something, then actually, in a perfect world, this would work just fine, and I'll take fries as an example, not to bash companies or anything. But if they actually had a decent inventory, their system would work just fine. Because you go online and you can say, the Campbell store has 2 of these. Okay, you go to the Campbell store and there's nothing in the store. Where are those 2 items? And it's not the technology's fault. It's the fact that someone stole them, or the people that take the inventory over there, or check stuff in when something gets received, doesn't get put into the database, or gets put into the database but someone takes it home with them, or not to say that everybody steals over there, but there was a high-profile case not too long ago of many employees being arrested for stealing at the Campbell store, actually. But long story short, the concept is good, because then you would know as a customer if you were driving to the store. Also, you would know if you were purchasing it, whether it was in a store, whether it was in a warehouse, because the concept is we don't need warehouses anymore either. We can drop ship from suppliers, we can take from a store. It basically saves the company a lot of money if you can share the information. The information sharing is done in a distributed environment, long story short. So by definition, what is a distributed system? One in which components located at network computers communicate and coordinate their actions by passing messages back and forth. Most enterprise applications and web applications fall under the umbrella of a distributed system. And we'll see, we're going to create a distributed system actually today when we look at the JDBC connection. So what does a distributed system provide in terms of the consequences or the pros and the cons? What we're looking at is the concept of concurrency. So work is happening at the same time on different computers and all sharing resources. I try to refer to that as transparency because concurrency, it gives us a level of things happening simultaneously. There may not be a global clock, which is kind of an interesting thing. And you see this, actually I see this on eBay sometimes. The clocks are sometimes off between some of the different items. You see the listing and then all of a sudden I look back and I go, the time changed. It's like an hour off or something, or it's like, and actually their stuff is pretty synced actually because they have to for bidding purposes and for tracking the transactions and everything that's going on. But in a transaction-oriented world, you have to create a fake clock, essentially. You have to, because you can't rely upon, and you think about the world, take the entire United States, we have, I don't know how many time zones we have, 3 or 4 different time zones or whatever. Hour ahead, hour behind, 2 hours ahead, 3 hours ahead. If I'm on the East Coast and I'm on the West Coast and I'm shopping on eBay simultaneously, who's going to get there first? Well, if you go by the local time zone, the East Bay person is going to beat me out by 3 hours every time. But they don't. So what clock is it? And that's one of the things you have to actually think about when you're building eBay, and eBay is an excellent example of an enterprise application because it's running on multiple different servers, it's tiered, provides global clock, provides concurrency, has independent failure. Have you ever gone to eBay and have it down? No, it's always going to be up. That's something you have to work into the environment in terms of the application. You have to have replicated servers or fault tolerance. You have to have something that goes on so you don't mess up the transactions or mess up the servers. So all computers on networks, they're not sharing the same time zone or clock. No notion of correct time, that has to be implemented. Independent failures, as mentioned before, faults in the network resulting in isolation of computers that are connected. It would be a really bad idea if your database server went down, and that was the backbone of your entire company. So you're going to have a replication of that, or you're going to have multiple servers that are going to be supported on that. There also has to be motivation to construct a distributed system or a desire to share resources, which is currently the trend. In the old days, nobody ever wanted to share anything. Now there's more sharing going on. So more sharing, more desire to share, more ability in terms of connecting. So some examples of distributed systems, if you've never seen one, you just crawled out from under the rock, the internet is one. So the internet, www, interfaces, email, file transfer is distributed. Intranet, firewalls, routers, and servers are all distributed systems as well. Mobile and unambiguous computers, laptops, handheld devices, mobile phones, smartphones, smart appliances, they're all distributed. Here's your typical portion of the internet where we have desktop computers, servers, and network links. And I can kind of go through this because you guys are graduate students. You've all seen the internet before. You've all used the internet. This isn't your first course in networking, hopefully. But just to refresh your memory on the concept of the internet service providers, this is what I'm saying. We've got some client server still going on in this distributed environment. We got a hodgepodge out there on the internet because we got backbones that connect client servers to distributed environments. And the client-server connectivity actually creates the distributed environment as well. Here's the typical intra. This is the inter, outside open to the public. The intra, here's where we can create some sophisticated EE applications as well in terms of separating it out. And we see the distributed computing in the intra environments because our email server is generally, hopefully, on a dedicated server, depending upon how big the company is. Maybe it's shared. Hopefully we don't have the database server, the email server, the web server, the application server, all on one server, on one physical piece of hardware, and then we have a power outage, and everyone goes home for the weekend, or home for the day, or something. Here's our portable and handheld devices in the distributed world. How do they fit in? Well, they're more client. They're more client. Handheld devices are sometimes referred, well, everyone's a client who connects. But we have the internet out here. We've got a WAP gateway, let's say a mobile phone that comes through here, wireless LAN that they're connecting to, a laptop, a camera, a printer. So as we become more connected throughout the times, we become a lot more distributed. And I say that mobile devices, going back to that comment I made about them being clients, they're not normally servers. Although you can create a hotspot, or what do you call it, a connection point, access point on your phone and connect. And a lot of people do this actually, especially in rural areas where you don't have connectivity and you must get on your computer to check the email and you don't want to use your phone. You actually connect your computer to your phone, and then your phone is actually a server in that case, and your computer is the client. So, which, you know, people do. And actually I used to do it myself until I figured out that I can just get one of those cards and plug it into my computer. You know, Verizon smart hotspot card, you know, and I don't have to connect to my phone anymore. So, but some people don't want to buy the cards or pay the price for the card. So, plus, you know, it depends on how much you're traveling and where you're going. There's internet access is almost everywhere now. It wasn't really the case in the past, though. Here's our web servers and our web browsers, just to review the concept of the different servers hosting, and these are the web servers that are generally providing up the local, the front end into the server, into the web servers. They're really referred to as web servers because they're really just providing HTTP interfaces and connectivity. And nowadays, we can actually dedicate an entire server to that. And if you're, you know, a Google, as an example, you're going to have server farms all over the place with tons of servers just to serve up clients. Because when a server types in www.google.com, they want the Google page to come up, and they want it to come up fast. And it does, actually. But every time you do that, do it 10 times, you're probably going into about 2 or 3 different servers, depending upon what kind of load balancing is going on, actually. Another challenge of the distributed system is that we're not all alike. We have a heterogeneity that comes on, a variety of differences that are applied between different types of servers. Microsoft servers, Sun servers, Apache servers, Glassfish servers, I don't know, 10 server. So we have networks, computer hardware, operating systems that are different, programming languages that are different, implementations by different developers for different programs and services. And then we have the concept of middleware. And middleware, how this fits in the big picture, it brings everybody together. It's the glue that holds the servers together. So it's the, you know, you go to the paint store or you go to the hobby store and you buy the contact cement and the glue. There's your middleware to hold your pieces together for your project. This is what you're doing, but you're doing it for the internet. And the software layer that provides the common abstraction as well as the masking of all of the different ones makes everybody the same, which is kind of different. Some people call the JVM middleware, not middleware. What's it making the same? What's it holding? What's it gluing together? Nothing. So if I were to say, what is the JVM, Java Virtual Machine, I say, that's an operating system. It's an operating system we're loading on top of an operating system. What is RMI? That's middleware. Because RMI is gluing servers together, gluing applications and servers and components together. It's providing the operating system, and we just talk to the RMI, and the RMI talks back to us. And all the components are located on different servers, different applications as well. Same thing true. This is what Common Object Request Broker is, CORBA. And I probably won't talk about that till the next. Probably won't get into RMI till session number 2 as well. But covered later in the course. Also supports single program because, you know, when we get into these guys here, we want to have some Java beans. We want to have some stuff that we can use in the RMI. So I'm going to kind of build the foundational stuff first, and then we have some pieces to work with by the time we get to the middleware. Mobile code sent from one computer to another to run on a destination, maybe a Java applet. Nah, not so much anymore. We don't have so much mobile code. Mobile code was, you know, you downloaded the applet, and the applet ran on your computer. You know how long it takes to download an applet these days? Well, not as bad as it was in the past, but not so good. More challenges. Openness determines whether the system can be extended and implemented in various different ways. Sometimes not every system is open, which is why, you know, a lot of people have been wondering for years, why is Java free? Why do they provide it? Why is Apache free? No one's ever commercialized it. It's all open. You need it. How are you going to get multiple development going on from different vendors and different people and different services and different technologies that supports the growth of the distributed environment is to keep it open. So as soon as you start closing it off, then you end up with issues. And that's one of the problems you get with the .NET environment, actually. It's closed. You're on .NET or you're on .NET. You're not flipping. You're either you're a Microsoft house or you're not a Microsoft house. And there's not as much openness. So the degree to which new resource sharing services can be added and made available to be used by a variety of different client programs gives you the openness. So don't try to do .NET development on a MacBook. Now, I think it can actually be done, and there's a beta out, actually, of a virtual machine that you can load to do it. Or you can install Parallels and do it from a virtual environment, but it's kind of complicated. It's not supported on every It's not supported on every operating system natively. So, open distributed systems have key interfaces published for them. The protocols are readily available, makes a uniform communication mechanism, publishes the interfaces to be shared resources, and construed from heterogeneous hardware, software, probably from different vendors, but all vendors conform to the published standard. Security, and we all know that one already. Information resources are highly valued. They have a high value to users. Everyone wants to break into the bank, break into the store. I would love to figure out how to break into eBay and just take everything. That'd be nice. But you can't do that. There's security. It's vitally important. Must have confidentiality, integrity, availability. Not a security course. If you're interested in security, take a network security course. In fact, I believe ITU has several of them that are offered by, I think Minwoo actually teaches all of them, which is good. So he's a really good security guy. Highly recommend his classes. Scalability, also an issue. One of the things you get with a distributed environment is you have more scalability. You have the ability to add more servers, separate stuff more out into more different locations. The system is scalable if it can remain effective when there is a significant increase in the number of resources and the number of users. Obviously, a decrease has no problem at all, unless you actually need to save money and get rid of some of these servers. But usually it's the increase is the challenge, supporting the growth. Some challenges might be controlling the cost of the physical resources, controlling the performance loss, preventing software resources from running out, avoiding bottlenecks. Failure handling, also another issue that is addressed with enterprise computing. More failure types can occur in processes and networks. Obviously, you have more points of failure. If it's all on one computer and the computer's running great, it's brand new, no problem. It's going to run for a couple more months or something, a year or so. When you distribute it out all over the place, you've got various different ages of servers, various different components maintained by various different people. You're going to have a failure, more likelihood of a failure in a networked environment. Failures are partial, perhaps. Some components might work, some may not, which is why transaction management is actually a decent component. So we want to be able to work with, and this is one of the things that RMI actually kind of gives you as well, the ability to maintain a current, consistent, persistent data and state so that if a server is down, it can be detected. If an application fails, if a database is not accepting a login, we can sort of hopefully detect some of these issues and deal with them. Techniques for handling failures. Some of it is detecting the failure, masking the failures, tolerating them, recovering from them. Maybe some redundancy in hardware. ATM machines are really good at that, actually, masking the failures. You know, have you ever gone to an ATM machine that says, I'm sorry, but this machine is no longer taking deposits, or this machine is not going to be able, and everyone in this room has had one of those messages come to you at one point. That's because there was a failure, because it couldn't connect to the central database, so it has no idea and can't keep any track of anything. So it won't take deposits and won't do withdrawals, but you can check your account balance. It's like, how can you do that? Usually you can't do anything on that machine, if that's the case. So. Or it's run out of money or something, or I don't know. Definitely don't know how ATM machines run, but I've always seemed to see those things there. Most of the smart tools, like, you go to the gas station and says, sorry, we're not being able to print receipts today. It's because it's out of paper. So that's a message that came out from a fault tolerance because it detected that no paper was in the dispenser. So. Concurrency, talked about this already, several clients attempting to access a shared resource all at the same time. How are you going to deal with that? We have the concept of program threads, and we have concurrency control and concurrency management in remote objects. And what we end up having is an RMI engine that handles concurrency for us, which is nice. So we don't have to actually implement that ourselves. We get it as long as we use the middleware platform correctly. Distributed software must be responsible for ensuring that clients, or servers and applications operate correctly. So here's the word I like, our vocabulary word for today, transparency. Means it's clear, concealment from the user and the application programmer of the separation of the components in the distributed system. That's one of the best features of distributed systems. They should be transparent. So that's when I say you can kind of see the not transparent parts when you get those weird messages that this machine can't take a deposit. It's like, ooh, now I'm thinking the machine is up. Why can't you take a deposit? Well, because under the hood there you lost something. You don't have connection to some component you need connection to. System is perceived as a whole rather than as a collection of independent components. If you have true transparency programmers only concerned with the design of their particular application, which is kind of interesting as well, which lends itself into nice island of your own application and development environments. But you do have to think of the big picture. Your application is working with somebody else's eventually. So. To reiterate the point about transparency, we have some different forms. Access transparency, that's the ATM machine actually, enables local remote resources to be accessed using identical operations. So when you stick your Wells Fargo card into the universal network and you stick your Citibank card in, it does the same operation regardless of what bank you're actually using. But I guarantee it, it's going to 2 different servers. So. Actually, it's probably going to an application server first, and then it's going to your bank location. Location transparency enables resources to be accessed without knowledge of their physical or network location, for example, which building or IP address. You get that when you type in www.google.com. Although it's a domain kind of feature, you actually have location transparency. You don't know if you're connecting to a server in San Francisco, one in Oregon, one in Washington. You don't know where you're going with that one. Concurrency transparency enables several different processes to operate concurrently during shared resources without interfering with each other. This would be the concept of 2 people using a shared gas card, as an example, both getting gas at the same time or something. So we have transparency in terms of the way that the transactions are concurrently occurring. And we have concurrency control and management that occurs with that. And also replication transparency when you go to barnesandnoble.com and one of their servers is down and you get routed to another server that is also housing the same application. It's nice, enables multiple instances of resources to be used to increase reliability and performance without the knowledge of the replicas. In fact, you get replication transparency with your ISPs these days. Customers don't like it when they can't get connected. You ever notice you always have a constant connection? You'll never lose your connection. However, you will be switched to a different server when your server is not working properly. After so many people have complained, they'll just switch you over, and then now you'll have tons of people on the server and you'll have slower access. So your access speed will vary on most of your ISPs consistently. I mean, different times of day and stuff with obvious just regular traffic flow. But on certain days or certain months or certain times, you'll notice it'll be lickety split and then it'll be really, really slow. That's because you got transparency going on with your replicated servers and which server you're actually connected to and which one they put you on. Web hosting environments have a tendency to do that as well. They'll move you onto a different server and you won't notice the difference. Your IP address will stay, everything will stay the same, but you'll be on physical hardware that's different than it was before. Failure transparency enables concealment of faults, allowing users and application programs to complete their tasks despite the failure. Here we can do your transaction, but you're not going to get a receipt. Is this okay with you? Okay. I get that like 99% of the time when I go buy gas. It tells me no receipt available. All right, I'll continue anyway. So, mobility transparency. This is what we're getting now with tablets, and we're getting with phones themselves, smartphones, tablets, mobile devices. and a good example of this would be something like Google Docs or Gmail as an example. And I check my Gmail on my mobile phone, and if I've read a message and I go to my computer, it's already read. I don't have to go back and mark it read or reread it. If I have it synced correctly on an SMTP server, I get what's called mobility transparency. Doesn't matter where I am, where I'm checking it. I've checked the email. I've read the email, and it's marked read on everything I check it with, because it's housed on the server, not on the device. So it allows the movement of resources and clients within the system without affecting the operation of the users or the programs. So the program knows you've read the message regardless of where you've read it from. And some of you who have PopMail probably don't have that feature, especially if you leave it on the PopMail server. So in the old days, when you checked your email on your phone, I always had to go back and sync it. Actually, Blackberries used to do that. You had to sync it so that your Outlook matched what was on your BlackBerry. And then they came up with wireless syncing. And then they got rid of syncing. There really is no syncing anymore. It's running like Gmail now, which is great because it's giving you that transparency. Scaling transparency. Actually, we're seeing this a lot with desktop computers as well. As you move all the applications, in fact, cloud computing is going to give us, desktop mobility transparency, because it's not on the computer anymore, it's on the cloud. So if the device, you go to the store, you buy a new computer, you turn it on, and it's your computer. There's no setup anymore, or in the future, there won't be any setup anymore, because it's on, your Microsoft Word subscription is on the cloud. It's on the application cloud. Your videos, your pictures, your photos, your music, all on the cloud. Nothing is on the computer. That's why I said this doesn't have to be fat anymore. This computer can be a monitor and a keyboard, and it can be lickety split thin, as long as it has good connectivity. And that's the only thing holding up that initiative. We happen to be living in, or some of you are living in California, some of you are not. Everybody has connectivity in California. Go to the Midwest. Not everybody has connectivity. How can you deliver software and reliance upon a high-speed access when not everybody in the world has it? So maybe another 5-10 years from now, when everybody in the world has access, we'll have clients that are like a piece of paper, as thin as a keyboard essentially, because that's all you need. You turn it on and you buy a new one, you throw that one away, you buy a new one, you turn it on, it's already configured for you, it's all ready to go. It's kind of like your phones actually. Your Android phones are running like that now. So you lose your phone, go get a new one. Put your new thing in there, turn it on, there's my address book, there's my telephone numbers, everything's all there for me. So, if you have it configured correctly, that is. Because there's a cloud. If you have Verizon, you're on a cloud. Everything is being backed up anyway. So depends on your provider right now. Not all phones are running that way, so not to mislead you. Scaling transparency allows the system and the applications to expand and scale without changing the system structure or the application. So here's a big picture. Here's the big picture I've been talking about for the last 45 minutes or so. I don't know how long it's been. We're going to take a break soon, don't worry. We've got customers and we've got partners up here on the top. And there's the customers and partners, and they're working with customer support as a department, inventory management, going back to my retail environment example, sales, is working with the database, we've got email out here, we have the HR department, fulfillment, we've got employees that work with it. Everybody's working with the same identical systems, and the systems are networked together to provide all the services for everybody. That is the true definition of an enterprise. So an enterprise works with customers, suppliers, employees, potential distribution houses and stuff like that. And we only have one customer service department, one fulfillment, one centralized database of the inventory. And we have data that's shared among all of the different systems. This is essentially the goal of modern day computing. Not everybody's there yet, believe it or not. Well, some people, believe it or not, there are companies today that still have separate databases in different departments. And they have separate applications and they don't share anything. About 5 years ago, 5 or 6 years ago, I had a guy in here who was doing consulting work for HP, and he was telling me that they have like 3 different, in one of the research development departments, there's 3 separate databases and they don't talk to each other. It's very hard to find information, according to what he was running into. And he's like, well, why didn't they just put it all on one server? Or why didn't they put it all together? I said, well, that's because HP is kind of an older company. So new companies, not like, to give HP a little bit of credit, they've been around for years. They have so many old applications, so many old things that have, if it's not broken, don't fix it. And it's a huge investment to take everything out and replace it with something. So newer companies, it's easier. You don't have anything. You're building it from fresh. You're building it. You can enterprise everything. So you got, supply chain management enterprised. You got customer relationship management enterprised. You got everything on an ERP system. You're not going to necessarily have everything broken out because you don't have anything to work with. It's kind of like people who get brand new internet access. The new construction that they have DSL wired into the walls. Older houses don't have that. You're lucky to have copper wire that still works on the older houses. So newer development is newer technology. You get the advantage. So just because a company isn't up to speed doesn't necessarily mean it's their fault. It doesn't necessarily mean they didn't think about it. It's just that they've been around a long time. Enterprise framework. This is the scheme for classifying and organizing the topics related to managing the enterprise. So assisting the organization to become more accountable, more responsive, shows enterprise architecture considerations, design, operations perspectives, things of that nature. And then now we're going to kind of move into our distributed systems architecture part of the lecture. As I mentioned before, I'm going to talk a little bit about architecture and design patterns a little bit. And trust me, we will break for lunch soon. So, architectural model, what is it? Defines the way in which components of systems interact with each other. Okay, it defines the way in which components are mapped onto the underlying network for computers, and it's the decomposing of the architecture of the distributed system with both vertical and horizontal tiers. So this is what I'm giving you in terms of the tiers. We need to consider layering and tiers in building this enterprise environment. So the application, the operating system, the hardware, these would be considered as a primitive example, layers or tiers with examples here. And you can substitute any platform you want down here for the Pentium, XP, the Explorer. And then we have tiering, in which we have, as an example that I've given you so far, the 3-tier system, where we have the client, and this would be the internet example that I've given you so far, the web server, and then the application server. The application server can be considered the persistence tier because it's delivering the persistent data. It's the application. It's keeping track of what the customer is doing and persistency, if that's a word. So each tier consists of one or more components that collectively fulfill a common purpose. So the client and the Internet Explorer is going to be working with Apache that's working with an Oracle database as an example here in terms of the client, the web server, and the persistent tier. There's other examples, however. That's not the only form of the 3-tier. And then we have the separation of the logical and the physical tiers in this architecture. So the physical tiers are based on the assumption that the application software components are found on different tiers that reside on different computers. So physical refers to the actual hardware of the computer, or the processors, which is interesting because we can have one hardware that have multiple processors running multiple applications on the different processors associated with it. Or logical tiers, which if the system deploys on a single computer which has a separate software tier to it, we're only going to, in this particular class, because we don't have unlimited resources here, we are not going to buy a bunch of computer equipment to logically to physically separate things out onto different servers. We're going to be looking at a logical abstraction of the tiering in this class. If we looked at the physical versus the logical tiers as an example, the physical, we have a server here, a client here that's running Windows XP. We have a Unix host, we have a Linux host, we have tons of different hosts out here. We can have multiple different Unix hosts if we wanted to. Logically, this would be the web browser attached to the Apache server, attached to the Oracle server. These are actually examples of entity relationship diagrams, by the way, as well. So a lot of the architectural designs are demonstrated, are mapped out, documented in terms of entity relationship diagramming. You know about that if you've taken my database class, actually. So if you don't, you'll hear about it in the future if you haven't heard about it already. So let's run through a couple of different examples to put this into perspective in terms of what we're looking at, here's the single-tier architecture. It's a student services application. And what we're looking at is the simplicity of it, providing convenient initial framework for subsequent examining more sophisticated multi-tiers. We're going to break this out actually in the next couple of examples into multiple tiers. This is a single tier. It's based on common functionality, where we have the logical client connecting to the logical server, connecting to the logical persistent application server. So this is the web server, this is the application server. Application server's got the file manager in here who's getting information from files, from data that's being housed, that's being sent to the server, the logical server area. So step number one here, this is the big picture, running on localhost, all on one computer. If we make it a two-tier, we'd break it out into a client and a server. So most two-tiered systems are client-server. Three-tier or above is distributed, and by definition. So and on our two-tier here, we can transform it. We can take the client, move it out. So we get the UI, the domain, all the information associated with the client that connects to a TCP/IP connection, let's say, to the server. And then we've got that. The three-tier, distributed. So now we have the client, the server, and the database server, or the file I/O that's brought out and put onto a separate server. So we have actually two servers now. One's going to be called the application server. The other one's going to be called the database server. And then here's a multi-tiered physical architecture. This is a large telecommunication company as an example, where we've got multiple clients, multiple web servers, multiple application servers, multiple database servers. This is more common in terms of what is referred to as a tier in terms, because then you have growth. You've got expansion. You just add another server if you have a bottleneck somewhere. You might actually notice something in common here, actually. This is common among all multi-tiered systems. This is going to vary. The number of clients will always vary. The number of web servers depends on the number of clients they're connecting to it. This is going to be changing a lot. This back here always stays the same. It depends on the app. We're going to have not as many application servers. It depends on the applications. It depends on what we're serving up. These guys, we don't have to have as many, because almost think of this like a funnel. As soon as we put everybody in a funnel, what's coming out, the big end, and all the clients are coming in, the request for the functionality is kind of small. It's one at a time, two at a time, dripping out to the bottom of the funnel. And here's the funnel tip, and it's just going to drip out to these application servers. And then these application servers, you can pretty much determine the database connectivity needs. Yeah? Very good question. The web server is going to provide the port interface for HTTP, for your hypertext transport protocol, for the actual delivery of the presentation of the information to the client. It's going to house up, it's going to support the scripting languages, the functionality to perform simple application-related or presentation-related details. And it's going to support the connectivity of the application server. Static pages, housing of scripts, housing of maybe some small data, reports, files, not application related. It's going to be for servicing up needs to clients. If you made a website, what you're doing, your mom and papa shop, you're going to go to GoDaddy.com, you're going to put together bhacker.com. Bhacker.com is on a web server. I bought some space for $9 a year or something like that, or I can't remember how much it is. And they gave me I don't know, 4 gigs on here. And I'm servicing up to you all my documents for this course. If I wanted to, I don't use it, but if I wanted to, I have access to MySQL. If I do that, then I'm going to go over here, and I'm going to be running PHP admin. Actually, PHP admin is probably running over here. I'm probably not going through an application server at all, actually. I'm probably going through, or if I am going through an application server, it's just for the connectivity to that database. The application servers, this is where you're going to get your supply chain management program, your customer relationship management programs, your accounting programs, your HR programs, all of the programs that a business would actually use in terms of its applications. Serverless could be out here, yeah. They're going to be running through an Apache. Think of this like the Apaches, the web services. Servlets can be out here. A servlet can call to a Java. Well, actually, let's not take that as a direct answer, as a yes is going to be here. You could design it to be on an application to serve up, and you could put your beans here, and your beans would be connected to, if you were combining that with a couple of other components, you could reside it here, you could reside it here. Actually, in all honesty, you could put it all on one computer. But when you logically try to separate out into physical devices, you're thinking about fault tolerance, you're thinking about economies of scale, you're thinking about where logically in the process should you put something. In this particular example, I would, if I had a small company, I'd probably put it out here, and I probably wouldn't even have any application servers. The middleware? The middleware? Is that what you're saying? Middleware is going to be in this area, but it also actually expands everything past the client. When you're connecting in, you're going to be looking at, and you're going to put the middleware, you're going to have it out, depending upon what type of middleware you're using, as the foundation to connect all the components. It's the glue that's going to hold all the components together, so you don't have to call another server. In the old days, and we're going to see it with TCP and UDP, you create a socket, you connect to the socket, you send a message, you receive a message, and it's socket oriented, and it's send and receive messages. And there's no, the session that's going on, the state of the message, the state of the connectivity is all manually controlled. RMI as a middleware application is a step above it. It's built on the socket concept, but instead of going out and establishing a socket, you already have the socket. And you already have information about the communication. You have, it's a step up above TCP actually, because it's managed and it's controlled. And we have error checking, we have a lot of different features that go along with it, and it replaces the concept of having to create the socket and use the socket. Because, as an example, if I did not have middleware, this web server would be going through a CGI port and making a physical call, creating a socket, going to the application server. And the application server would be creating a socket and establishing a connection and going over and talking to the database server, and then closing the connection, and then closing the connection. It's like taking multiple buses instead of getting on a direct route. Where you got to stop here, wait 10 minutes, stop here, wait 10 minutes. It's like taking multiple flights with layovers instead of a direct flight through. If you take the direct flight, you're going to get there faster. Of course, it's cheaper probably to take the multiple layovers for flying because sometimes you can find better deals on the connection points. So, and actually, believe it or not, it's kind of the same in terms of networking, because it's cheaper because you don't have to install RMI, you don't have to stick the resources or anything. But it's saying, and you can mix and match and pick and choose what kind of protocols you want to use for the socket creation and stuff like that. So, but it's going to take you longer. It's going to run slower. So, actually, it's a good analogy. I just thought of that. So, but the abstraction of it is usually past the client. Everything's past the client. How you divide it out depends on your tiering technique. Very good question, actually. Here's our middleware, some examples of our middleware. This is where we're going to have our DCOM, we're going to have our web services, we're going to have our platform itself, the platform layer, the hardware, the middleware. And the middleware is just something that lays on top, sort of like an operating system, actually. That's why a lot of people call it the JVM middleware, when it really isn't. It's an operating system on top of an operating system, but because it's not providing any connectivity. So here's an example of student services, and let's bring enterprise Java Beans into this as the middleware. So while contemplating the design of this new student services application, we're going to take that new student services kind of an example. You don't have to worry about remembering what it looked like, because you'll see it again. Realizing that you're going to use a middleware platform will result in more robust applications that can be developed in a shorter amount of time. Not only that, but if you don't like the functionality of a bean, you can swap a bean out with another bean. It's not like taking, in the old days when you took and created, before object orientation came around, you created a procedural imperative language application. It was a C program. You had pages and pages and pages of source code, and if there was a bug in there, you had to recompile the whole thing. Not the case anymore. If you break it out into separate components or objects, you got a problem with the object. Everything else stays the same. You just take that object and replace it with a new object that has the same public interface that works the same. Same thing you learned in the Java in the object-oriented programming in Java course. It's reusable, swappable, more maintainable. So a web survey, let's say, identifies 3 major contenders here. These actually all work. I tested these links out. And if you wanted to look at, let's say, what would be considered a middleware, sort of the Enterprise Beans, the Enterprise Java Beans application server, and we'll talk about a lot more about that in detail, probably not until the second class meeting. .NET, I'm not going to talk about that at all, or W3's web services, we're not going to talk about that either. But these are some examples. If you were looking for some additional reading, this is where I say I don't have a textbook, but I can definitely give you resources. These are some areas where you can learn a little bit more about the differences between the different middlewares if you're interested. And here's an example of the tiering put together. So multi-tier architecture with the student services utilizing the EE platform. This is what we're the logic that we're thinking about in this particular course. We've got the tiers for the business logic, and the student uses XP, let's say, for example, might be using MySQL, might be using Oracle, might be using all sorts of different databases from the persistent level. We're just taking the business logic, separating it out, putting it in a separate tier. And this is the application level, or the business logic. So you might think of applications as businesses, business logic, business programs. And then over here on the end is the data, the persistent tier. So we have component transaction monitoring that occurs. So the component transaction monitor, what in the world was that referring to? Well, it's the server-side application that combines the features of the traditional transaction monitoring and more. It actually has to, for recent distributed object request brokers, ORBs. So in the component transaction monitoring, it's kind of similar to transaction monitoring or transaction control or concurrency control. But it's keeping in track, and it's basically aware of the objects and the instances of those objects and the services of those objects that are providing for the big distributed picture. And it's allowing you to have a little bit more control and management over those services and what's going on. So a TPM is an example, or ORB is 2 examples of this component transaction monitoring concept. And these are just 2 primitive kind of examples. ORB emerged to support the deployment of objects across the network, and RMI uses an ORB. So as I mentioned before, the object broker, what RMI is going to do is essentially allow you the ability to keep track of the states of those objects, who's got access to those objects, privileges of the objects, and then which objects are loaded, which objects are not loaded. Because in a particular networking environment, if the object is already there, why make a new instance of it? So keeping track of the instances and the states of the objects is important. So something you get above and beyond creating a socket and sending a message. You get a broker, object broker, who's going to serve up objects for you and keep track of their states and who's accessing them and log all that information for you, which is what we're going to see with that RMI. And it gets into the concept of the object lifecycle. So life cycles of an object is the life of the object from its creation, its modification, its deletion. Object instances is the core to this concept. Not domain data associated with the application, not saved data, but object instances. If you think about the concept, objects have a life. They are in existence, so they can be managed in a real-time kind of fashion. They're not data. They're not stored data. Saved data in terms of the application. They're object states or object instances. And then we have this new, and this is where I said I'm going to give you a little introduction to design patterns, the concept of the factory. The factory design pattern. So it's often used to encapsulate the functionality associated with the lifecycle maintenance of an object. So if you think of the concept of a factory, it's like the creation of the objects and the management of the objects. It's like the worker bees in the factory. The objects that are doing the work for the application. So think of them as think of it as a factory, actually, in terms of the definition of what a factory is. It's a workshop. It's a work environment. We've got people to manage, objects to manage, and the life cycle of the object. And who's been created, who's been assigned, who's on shift, who's off shift, who's doing what, who's servicing up, who's working. Patterns. So this pattern separates the business logic of the domain being modeled from the object's life cycle. So we have the factory design pattern, and here's a sort of an example of it. Student factory contains methods for creating, finding, and removing a student object. So it's methods for creating, finding, removing, manipulating, controlling object instances. So the student object contains operations associated with the domain application. As an example, adding a course as a method. And these would be the method calls that this object would be providing for requesters who came in. So as an object broker, this object would you'd request something of the object, and the object would give it to you, hopefully, through method calls. Same thing that you've learned so far, you're just taking it to a different level. So we have create, find by name, remove, stuff like that. And here's an example of the student factory in a distributed system using a singleton design pattern. So the factory can be conveniently implemented using what's called a singleton. And you get this terminology a lot with if you take a design patterns course, Java design patterns. You can get it with Visual Basic as well, and some other different Visual Studio, I meant to say, application. So the patterns as shown in this particular example, what we're looking at is hiding the actual location of the business object from the user. So kind of a single location sort of thing. It might actually reside in multiple, two different student objects located on the different server, where we have a student factory, who the singleton is going to create a student factory, a new student factory, and we have a new student factory, all residing on let's say the same server, or different servers that are given you in terms of the design. The new student object can be created using the Java, and here's just creating of a new get singleton.create. So the concept of there being actual two student objects instead of one, let's say. And then I've talked about this so far already, the concept of the persistent tier, and I mentioned it, it's the data, it's behind the application tier. We call it the persistent tier because not everything's a database server. So it's the tier level that the database actually sits on. Some people call it the data tier, but it isn't really data, it's persistence by terminology. So by definition, in multiple tiered environments, the persistent tier encapsulates the logic of saving the data to and loading the data from persistent storage. So don't walk away with the impression that it's always a database. It doesn't have to be. It could be a file server. It could be an application that's working sort of like a database that's keeping track of information. As an example, in an eBay kind of environment, if you have, if you think about the concept of what's going on in that application, you got lots of people placing bets, looking at stuff, creating watch lists, and all sorts of stuff. If you're really going to store that in a traditional style database, the updates, the size of that database would be incredible, especially when it's all temporary data. It goes away. It doesn't last forever. I mean, of course, there's a history that sticks around. But if you have another type of service that is actually running on a persistent tier, it's saving the state of everything. And maybe it's just in a temporary format, or it's in a proprietary database-like, but not necessarily long-term. It's a short-term temp kind of a thing. That would run a lot faster than reading and writing to a database every time somebody put an item in a watch list. But if you think of the concept, millions and millions and millions of users, each one of us has our own watch list, our own wish list, our own betting. I mean, that's a lot of data exchange. I don't think it would actually be implemented properly in a database. You'd probably wear out the database in an hour or so. You'd fill it up with so much data, it would be incredibly hard to even query. But if you have a persistent tier configured to save that data in some sort of a fashion that was more efficient, that would probably be a better solution. So don't think of it like it has to be a database. It doesn't. So within the application level, the tier for the constant state information, the enterprise information, the business logic tiers is representing using remote objects. Some of those objects are beans. Some of them are just objects themselves. As with all objects, A remote object captures state encapsulated by local data, sets of attributes, consequences. The object requires saving its attributes values to non-volatile storage. So it does normally contain saving information to something. So in terms of the persistent tier, some examples here. We have the Java serialized objects. We have local files using XML. Actually, XML is not a bad technology to be familiar with as well, because you've got XML being used with persistent data constantly. Because how are you going to send from the application server if you've got database, let's say a database that you're going to connect to, and you're going to send, probably going to send it from a web server, actually XML, into the database server. And it's kind of like, if you're not familiar with XML, you haven't taken a web course yet, it's just like HTML, except for instead of mocking up and presenting text to the user, you're mocking up and you're presenting data to an application server or to a persistent tier to exchange the information back and forth. So these design patterns are developed to capture the saving of the data to the files or the database in this particular case. One of the most popular design patterns out there is the data access object, the DAO pattern, which is basically a kind of a way of describing the capturing and the saving of the data to files or to a database. And that's very common in most applications that you're going to create. So it's called a DAO. So what is the design pattern? Well, it's a pattern providing a generic reusable designs that solve problems at a design level. It's kind of like how you have a programming pattern. When you write a C program, your design pattern is to have a main. You have to have that main. If you don't have main, your compiler's going to complain. Well, in the configuration of this big scheme with the object brokers and stuff, your design pattern is going to give you this template, and that's not really call it a template, but the pattern to compose different components to get the functionality to work correctly and reliably. And these are just suggestions. You don't actually have to follow design patterns, but it's nice to be familiar with them. You can take an entire course in design patterns and still not actually get all of it, because things change as well. Things get updated. So it provides a proven testable solution for a class of similar design problems. How are you going to connect it with a database? Well, you're going to do this. And I'm going to show you a design pattern, actually, that's a programming-related design pattern after lunch. When we look at JDBC, I'm going to save the JDBC stuff. In fact, this lecture is going to be over within about 5 minutes or less, for some of you who are nodding off already. So lending a common terminology that can be used to make your own designs easier to document and understand as well. So it provides a common language for developers to use in meetings, documentation and stuff. So here's another example. We have our factory that uses our database access object. It could be a bean, it could be an object, it could be something served up. We have our database object, our business object here, that uses this database object, and we have a data object, and then it uses our persistent manager. It goes back to our persistent tier. And this is nothing more than a way of describing how we're going to use an object to access the data. Because what we don't want to do is hit the database with a ton of requests. I mean, that's going to be a bottleneck. Because going back to the concept of the tiered environment, we're trying to reduce bottleneck. We're not only trying to provide for transparency, but we're trying to provide for efficiency, which is the reason why we're doing this. If all of our requests go into the database and the database is getting 1,000 hits on it, we're going to have an issue because the database can't serve up that fast. So that's going to be a bottleneck. One bottleneck, we're only as strong as our weakest link. So we remove the bottleneck by creating a common DAO object that's going to essentially serve up requests to the database, control the access to the database, one single point of queries, can save it all up, can send it all in one pass, can basically make efficient use of the connectivity between the object and the database. So in terms of the design pattern for the DAO, this is a separate business logic aspect of an object from the code used to access the persistent storage, actually. We separate the logic out into a separate object component. In a distributed system using a factory to find the remote object doesn't allow us, or it doesn't always require loading the object from persistent storage. It might have a different functionality to it. Could have been previously loaded as well, or it could also have been found on the network somewhere else. So it may not have come from our application. It might actually be from a different location. Here's an example. When a student object is sent a message to save itself, the student will delegate a request via a message sent to the corresponding data access object to perform the saving. So it knows to save the object right to a particular database system. Maybe we have multiple databases that are being used. Very typical. In fact, we could even have an Oracle system with a MySQL system with another system. Well, the data access object is going to know which object to go to for that particular transaction that's occurring, instead of having the application hard set it. It's kind of like if you were to write an ATM program. Are you going to write a program that's going to detect all ATM cards from all banks? What happens if XYZ Bank opens up across the street and it's a member of the Star network? It puts the card in there. Is it going to know XYZ? You're not going to hard set the server location and all this. And so you're going to implement an object, and the object's going to know all that stuff. You separate it out into a design pattern so you can easily expand the system, grow the system to accommodate future changes that are going to happen. So it adds the concept of using the design pattern actually provides more flexibility as well and more growth in the system. That's another selling point. And here's just the expanded version of it, where we have the DAO factory that's going to serve up, and what we got here, the factory object here, the database object, XML file directory, the factory that's going to serve up the pages. If you're not familiar with XML, don't worry about it. We're not really going to use it very much in this course, but it's not a bad technology to be familiar with. So let me see, how many more slides do I got here? Okay, we got 2 more slides left. I'm hungry. I'm waiting for lunch. So, so the DAO, I'm going to finish this up in 2 more slides. So the DAO factory pattern here is often used to further separate out the application server from the persistent engine, as we've seen. And as an example here, considering the situation in which we have data that might be saved either in a relational database MySQL database or might be in an XML file. And the database access object is the one who's going to be able to have that logic built into it to determine, is it going to the database, is it going to the XML file, things of that nature. So what do we have here? Anything important on this slide? Let's see. Well, I'm just going to explain the next example. So the business object, such as the student, would request data access from the object from the data access object factory, would know and serve up the right one. So here's I'll just explain it with the example. So if we have a student and we have the student data access object and we have the SQL is going to run the query object, we could actually tier it out. The data access object would actually implement another object that would be performing the queries, and the queries would be deciding in the JDBC connection, would be housed in this particular object, not in this one. And the JDBC connection would be connecting to the databases, and to the external other servers on the persistent level, persistent layer, I should say. So long story short, we're using these objects to break out the functionality. Just like we create Java programs with multiple different objects, think of it the same thing, except for you're looking at it from an enterprise perspective and from a tiering perspective. So what we're doing throughout the course is essentially deciding on which objects are we going to create and how we're going to do it. That's probably the most difficult part of designing an enterprise application, because essentially that's the core of the application. How do you have it broken out? So having investigated the benefits of the DAO approach to persistence, and you decide to update your student persistence to use the DAO and associated factories. So while developing your design, you realize that you're not exactly sure how the student data access model should be implemented, but you remember JDBC, and it can be used with Java and object and relational database, so you have the DAO use JDBC. And JDBC is going to be covered after lunch. So what I'm going to do now is we're going to decide how long we want to take. Actually, before I do that, I'm going to stop this video because the people at home don't need to hear about all this stuff. So, in this video, if you've fallen asleep through half of it or something, or if you came in late and you missed the first part of this, it's all being recorded, so you can watch this, and I'll make the link available. So let me stop the video for now. The next one is going to be on JDBC. It's going to finish, just in case I'm not going to see you after lunch. Hopefully I will. I'm going to go through JDBC, the boring PowerPoint. Then I'm going to pull it out, show you. We'll go through some sample programs. If you have a computer during your lunch break, if you want to, if you're so inclined to start working today on stuff, I have actually last night I put some videos out there on how to install the JDBC drivers. But you're going to have to install Oracle or MySQL, and I'll go through that after lunch. I'm not going to go through the install technique because it would be boring to everybody sitting here without a computer. But if you do, you could possibly work on it after lunch or during lunch. You probably download the drivers and stuff. But not a bad idea to take a look. They're on the YouTube site, actually. I don't have the links, but I'll probably put the links up during the lunch break. Long story short, let me end this video. Next video will be on JDBC and examples.